All right, in this section, we're going to start picking apart our polynomial functions. And before we are looking at quadratic functions, and that's an example of one specific type of a polynomial function. But now we could have, the x cubed, x to the fourth, x to the fifth. So we're going to have higher degree polynomials in this section. So a polynomial function is of the form f of x equals a sub n times x to the power n plus yada, yada, yada. I'm going to let you guys read this. But basically, it's going to be a string of terms with real coefficients and then variables with whole number exponents, meaning they have to be positive numbers. So first, we're going to talk about what's called the end behavior. The end behavior of polynomial functions. So to do this, I want to look at a couple of graphs and compare them just to see how they're different and how they're the same. So I've got these kind of rough sketches over here of these graphs, but we can also pull them up in the graphing calculator. So over here on the left, it says graph y equals x squared. So let's go ahead and do that. Y equals x squared. And then how does the end behavior of y equals x to the fourth? So I'll graph that as well, x raised to the fourth power. How does that compare to y equals x squared? All right, so the guy in blue is our y equals x squared function, and the guy in red is our y equals x to the fourth function. It just gets bigger faster, so it rises more steeply. But when we're talking about end behavior, that means just out to the edge of the function as it continues. Basically, is it going up or is it going down? So over to the left of both of these functions and their extremities, they're going up. And for both of these functions, as x increases as we go to the right, the y values are increasing, they're going up. So the end behavior rises to the left and rises to the right. And this is true for y equals x squared. It's true for y equals x to the fourth. So what we'll see is this in general is going to be true for y equals x raised to some even exponent. Y equals x to the eighth would have the same end behavior. All right, and then going to the right here, graph y equals x cubed. How does that compare to y equals x to the fifth? So let's go ahead and put these in our calculator. Y equals x to the third and y equals x raised to the fifth power. Okay, so the blue guy is y equals x cubed, and then the red guy on the graphing calculator is y equals x to the fifth. Again, with the higher power, y just gets bigger faster, so it rises more steeply. And again, for end behavior, we're just talking about the behavior technically as x approaches positive or negative infinity as we go to the far right or the far left. So looking at the left side of this function, we can see as we go to the left on our x-axis, our graph is falling in both cases. And as we go to the right, as x gets bigger, y also gets bigger. It's increasing. So we can say that this graph, for both of them, falls to the left and rises to the right. To the right. Okay, so this is true of y equals x cubed. It's true of y equals x to the fifth. And what we'll see is this is true for y equals x to an odd power. All right, so in general, it says uses rises or falls in each blank when an even power function, so even, that's the exponent, even power function is positive, meaning there's a positive coefficient. The graph rises to the left and rises to the right. So when I see an even power function that's positive, I just think of my basic function y equals x squared, and I think of how a parabola behaves. When an odd power function, meaning the exponent is odd, when an odd power function is positive, so positive coefficient, the graph falls to the left and rises to the right. So when I see an odd power function that's positive, I think of the end behavior of y equals x cubed, and that's how I picture my end behavior. Okay, so now we'll do the same thing with negative coefficients. So now we've got y equals, clear that out, negative x squared, and then negative x raised to the fourth power. So now we have these upside down, in the x squared case, upside down parabola. So y equals negative x squared is the blue guy on the graph, on the graphing calculator. The red guy is y equals negative x to the fourth. So again, the end behavior matches for these two different power functions. The end behavior, as we go to the left and to the right, we can see our graph falls to the left and falls to the right. Okay, and in general, this will be true whenever you have y equals negative x raised to some even power. So if you have a negative coefficient, x raised to an even power, you'll see this similar end behavior. And finally, let's look at y equals negative x cubed. So I'll clear this out. So y equals negative x raised to the power 3, and then y equals negative x raised to the power 5. Okay. So looking at these graphs, both of them have the pattern that they're y equals negative x to some odd power. Both of them, as x goes to the left, our function rises to the left. And as x goes to the right, we can see our function is falling. Okay, and that will be true of any function that has that basic form y equals negative x to the odd power. So filling in the blanks, when an even power function is negative, has a negative coefficient, then the graph falls to the left and falls to the right. And when I have an even power function that's negative, I'm picturing y equals negative x squared, my upside down parabola. Then when an odd power function is negative, the graph rises to the left and falls to the right. So there I'm picturing the behavior of y equals negative x cubed. All right, so number one, without graphing, determine the end behavior of each polynomial function. So in A and B, these look way more complicated than what we just looked at, right? So what I want you guys to focus on is what's called the leading term. I want you guys to look at the highest exponent, so the degree of the function. The highest exponent, that term is basically going to dictate the end behavior of the function, because that large exponent, like x to the 9th, for example, because that x to the 9th term is going to get so big so fast as you're putting in different x values, bigger x values, it's really going to overtake the end behavior, the extreme values of your function. So we're basically just ignoring the other three terms when it comes to end behavior. We're just looking at that leading term, the highest power term. All right, so we've got a positive coefficient, right? Both of these are positives. Y equals x to the 9th is like a y equals x to an odd power function. For that, I'm basically picturing y equals x cubed. And if I just do a quick and dirty sketch, looks something like that. So I can see from my y equals x cubed function, this falls to the left and rises to the right. And of course, you could double check this in your graphing calculator. You could type in this polynomial into your graphing calculator to check it. But it's a little more straightforward and a little faster just to do this comparison to your y equals x cubed function, in my opinion. Plus, especially with these polynomials, sometimes you really have to zoom out and mess with your frame to really get an idea of the end behavior. So even though this might seem inefficient, I promise with some of these polynomial functions, when you get into your graphing calculator, it's a lot easier just to imagine the y equals x cubed function and know that the end behavior is similar. So for B, you've got y equals negative 100x squared times x plus 2 squared times x minus 3 squared. Even trickier, right? So in A, we had all these individual terms, and it was really easy to see what that largest exponent was. Here we have to imagine expanding. I don't actually want you to, distribute all of this out because you'll be here for a while, but just imagine expanding has a D in it, expanding this out. So you'd have negative 100 x squared, and then when you FOIL out x plus 2 squared, you'd have x squared plus blah, 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 And then for x minus 3 squared, you'd have x squared minus blah, blah, blah. Okay, we don't care about those final terms. We just care about the first terms. And then as you multiply these guys together, your first term would be x to the 4th. X squared times x to the 4th, blah, blah, blah. And then when you finally multiply in your x squared out front, you'll have negative 100 times x to the 6th. Okay, multiplying these terms together. And then blah, 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 blah. We don't care what happens after that. Sorry, that's so messy. Okay, so this is basically our leading term, negative 100 x to the 6th. So we've got that negative sign out in front. We've got an even exponent, so this behaves like this. And when I think of this format of my function, I think of y equals negative x squared, which is, just doing a quick sketch, that upside down parabola, that downward facing parabola. So that means my graph, my end behavior, falls to the left and falls to the right.